Okay, I think we're going to get started here with session number 2. I'm pleased to be able to present Guimei Wang. Come to the stage. So Guimei graduated from Peking University in 2008 while working on energy recovery LINAC-free electron laser beam design and beam physics studies at Thomson Jefferson Lab. In 2009, Guimei joined NSLS2 and worked on the injector system with a focus on optics design, linear beam dynamic studies, high-level application tool development, and commissioning activities. In 2013, Guimei became the coordinator for storage ring and insertion device commissioning. She led the top-off control testing and coordinated all major machine developments to improve beam performance. Guimei is now the Accelerator Coordinator Group Leader at NSLS2 and is responsible for coordinating operations associated with 28 beamlines and accelerator studies. Today, she is going to be presenting information on beam stabilizing requirements for ultra-low emittance circular light sources.
Thank you, Tonya, for the introduction. And thanks for the Scientific Program Committee for the invitation. And also thanks to the local organization host this amazing meeting. And it's really great to meet with everyone here. So because this is a review, I will cover many aspects about the beam stability. I would like to thank the many colleagues in our light source community for their fruitful discussion and the information they provided that contribute to this talk. And some of you are in this audience. Thank you. So this is my talk outline. First, I will talk about the requirement on the beam stability. Then we'll start to talk about how we can reach high beam stability, including the sources that perturb the beam stability, the diagnostic system we will use to monitor and characterize the beam stability, and a feedback system that can increase the beam stability. So from here, we can see the emittance trend since 1990s to the future 10 years. In 2016, makes for successful commission. That's really opened the new generation light source era. And since then, it transferred from third generation to fourth generation synchronous light source. The storage lattice design changed from the double band, triple band achromatic lattice to the multi-band achromatic lattice. Following their success recently, ESRF EBS and series also has been successfully commissioned and in operation. So now we are here. Looking forward the next 10 years, what is going to happen? We can see that many of the light sources are on the way to upgrade or is on the plan to study the upgrade method to try to push the horizontal emittance to the diffraction limit. Overall, we can see that the emittance reduction has been changed about 2 order magnitude. This is driven by the photon beamline users. They want to have a high brightness and high coherence. What does high brightness and coherence means to the photon user? That means they can get high spatial resolution and higher energy resolution. They can do faster dynamics beam study. To reach this high performance, beam stability is a crucial parameter to define the experimental resolution. So how does the beam stability affect the emittance or the, so the beam stability, the electron beam stability, it is driven by the photon beam stability requirement. With the emittance, horizontal emittance push from nanometer to 100 or 10th picometer radius. That means to the photon beam, it has a higher intensity, higher brightness, and also smaller beam size divergence, and also high coherence. This also helps the users to get a larger data acquisition range, expand from microsecond hours to hours, and also they can do the faster detector. Means they will push the faster detector sampling rate to kilohertz or up to megahertz. They also can get the high energy resolution. Those photon beam property matrix to the electron beam, that means we need to have the better position, stability, better angle stability. Usually we use a few % of the beam size or divergence, and also the large bandwidth feedback system to match the detector experiment with their faster sampling rate. Well, they also require the beam size, emittance, and energy stability. So in this talk, I'm going to only focus on the transverse phase stability and also time domain stability. So with the emittance 10 to picometer radius, the beam size and divergence will follow to a few micrometer or few micron radius. This will push the tight beam position or angular stability to submicron. In the time domain, it depends on the experiment sampling rate, data integration test period, and also scan duration. So this requires the beam stability span from hours to microsecond. In this slide, it shows how does the beam motion affect the beam emittance increase. We split the beam motion into the fast motion and the slow motion. Those fast and slow is really relative to the beamline experiment. So depends on sampling rate and also data integration period. So that means even it's the same motion to different beamline, they can mean different between fast and slow. Faster motion means motion is faster than sampling or integration rate. In this case, the beam distribution will smear out in the phase space and increase the emittance in this expression. And then 10% of emittance increase corresponding 30% of the beam size. So this kind of faster motion, usually beamline cannot detect and has a loose tolerance. But for the slow motion, which is comparable or less than the user data integration rate. What does this mean? So this shows illustration, how does the phase space change. The black curve is shows beam perturbed emittance. The red shows a beam centroid motion. So at different time, for the beamline that collects the data, they may see the phase space jitter around in this dashed curve. Overall, short to short or sampling to sampling, they may see the beam phase space paves around the whole yellow area, which we call the effective emittance. So the effective emittance increase can express in this equation, and then 10% of the effective emittance is corresponding 5% of beam size motion. So we can see the big difference between fast and slow means to the user. This slow motion, it is more serious to the user because it can introduce the measurement noise. Then our machines mostly focus on this sensitive frequency motion or the slow motion. We define as bounded of the high end by data sampling rate and the low end by data integration period. So in the following, I will present a few examples to show how does the beam stability affect like high spatial resolution, high energy resolution, and faster dynamics type of the experiment. And here is an example from hard X-ray nanoprobe imaging beamline in NSLS2. It is to provide X-ray imaging with 10 nanometer spatial resolution for the nanoscale material characterization. This beamline is about 100 meters long. So with this secondary source aperture here, it focuses down the beam down to the sampling to the nanometer size. The demagnification factor is 3 sound. With such a significant source demagnification, those type of the beamline are not sensitive to the position stability. However, they are very sensitive to the angular stability. And this angular stability limits the resolution of the differential phase contrast image. And to reach the beam stability at sample down to 1 nanometer, it requires a beam angle stability, 100 to 10 nanoradius. The photon source, motion source can come from the electron beam motion, optics, cooling, flow relative drift, or thermal drift, etc. This can overall contribute about 200 nano radius angular motion. What we did is we implement the photon local feedback and active beamline component feedback on the XBPM and maintain the long-term drift stability within 20 nanoradius. In fact, Peter Ilinsky is one of the main person to do this feedback system. And then here shows the image, how does beam stability affect the imaging resolution. The left one is without feedback, the right one is with feedback. It has a great improvement with beam stable. And this is another example with a high energy resolution. So this type of the beamline, SIX, it studied electronics excitation with ultra high energy resolution, 10 millieV at 1 keV photon energy. And then this beamline has two here. One is grating, one is exit slits. Those two together combined can select the desired energy bandwidth. This exit slits vertical aperture. It defines the energy resolution and limits the beam stability. We cannot put the slit aperture as small as possible because that's basically limited the photon flux. So in the current, they put the 5 micrometers vertical aperture and reach 10 to the power 5 resolution. And then it requires the beam stability at this slit have to be submicron. That means 10%, usually 10% of the slit size. The motion source, mostly in this beamline, is cooling water on the mirror. It can cause 20 micron movement at the slits. And the measure we did is to improve the noise source. In this beamline, it's special because it's soft X-ray. It's lack of non-invasive photon position monitor, and we cannot really implement the feedback from beamline side. And this shows, experimental result. They have achieved 23 millieV. The results are published in the Nature Material. This is a third example to show the fast dynamic study use coherent scattering. They can study the nanoscale dynamics using photon correlation spectroscope with hard X-ray coherent flux. And this beamline, they have two aperture here. One is to limit the intensity, another is to limit the coherent flux. So both of these combined together require angular stability less than 50 nanoradius. And it also, because it uses 2 times correlation and faster dynamics process, so it requires a shorter and long-term stability span from 0.1 millisecond to 6 hours. Their sampling rate up to 9 kilohertz. Then in the future, they try to push 1 microsecond. Those motion sources come from electron beam, cooling water, cryocooling on the mono and thermal drift. We implement the ID local feedback and active beamline feedbacks to reach the short and long-term photon stability at those aperture. And this show example earlier time. We don't have feedback system, and this beamline cannot get really any correlation at all. And this shows later with feedback system on, they can reach both short and long-term stability. So that's examples. How does beam emittance affect the high-performance beamline? Now we are going to talk about how we can reach the high beam stability. First, I'm going to talk about what are the sources that perturb the beam stability. The source of the perturbation can come from the natural or the cultural noise, and those noise can separate into different categories because they means different on the orbit or beam size. In the long-term perturbation, it can last from weeks to years. They come from the ground settlement, season ground motion. For the medium term, it can minutes to days due to the day thermal cycle, Earth's tide, or the beam intensity filling pattern. For the short term, it's milliseconds to the seconds come from, such as ocean wave, ground vibration due to traffic or trains, rotating machines like a cooling water pump or air conditioning, power supply noise, or ID gap variation. For the high frequency, such as milliseconds range, it comes from synchronous oscillation, injection transition, or the beam instability. So this picture shows how is a motion propagation. So it comes from site, then go to the building, go to the gutter, then gutter transfers the motion to the magnet, BPM or IDs, and then they affect electron beam motion. On the other hand, the power supply, stability, air conditioning, or cooling water also affect, feedback system also affects the electron beam stability. When the electron beam passes through ID, it radiates X-ray. Then X-ray goes through the beamline optics to the detector. Beamline optics can also carry the building motion, AC or cooling water, so the detector will see both electron beam motion and the beamline optics cause the beam motion. So this shows typical what is electron beam spectrum looks like, and in fact each peak corresponding different source of the motion, and then we have different measures to improve the beam stability. From this whole picture to see the noise source, we can improve some building design, we can improve the girder mechanical design, we can advance in the power supply stability, we can also advance the BPM and feedback system. So let's go to next, how will we do the building design? You know, the site selection is always the first line of the defense. Quiet site always preferred. However, it depends on natural soil, proximity to the highway, railroad, or the industry complex, how far we are away from the ocean, like National Synchronized Source, so we are only 15 kilometers from Atlantic Ocean. And this shows a different facility, their side of the ground replication comparison. We can see that Spring 8, it is quite a stable building among many of the facility. This is because they build on the firm rock. But for other machines, it's not always possible to select the site. Then the next level is we can optimize the building design. We minimize the noise effect. This includes we can isolate the base structure, try to avoid the vehicle tunnel or utilities, because those tunnels are very sensitive to the outdoor temperature or the tunnel temperature. We try to separate the fabrication equipment, isolate them from the storage room, such as a water pump or the motor rotation reduction. So this shows an example, new light source series, how did they do the building design? They separate storage room floor from experiment floor by using the reinforced bar joint. They all use the floor slabs to increase the building rigidity. And on the roof, they use a rubber band to smooth out the wind effect. Overall, they achieve about 11 nanometer noise level. So this is a good example how to improve the building design. And for the next level is we can improve on the gutter system design. So environment pass all the beam motion through the gutter, including the ambient motion, traffic, buildings, or pumps. So the gutter support system design is not only required easy installation or precise alignment of the magnet, we also need to have the high mechanical stability, that including the fabrication stability and thermal stability. Different facility, they choose different design, different support system. So for the vibration stability requirement, here shows an illustration how is the motion propagation from floor to the magnets or the BPM. The transmission ratio defined as a magnet vibration amplitude versus floor source motion move amplitude. This depends on, so the transmission ratio depends on the gutter rigidity and also depends on the natural frequency of the gutter design. We can see that with a high rigidity and it can have the lower transmission ratio. And if the source motion frequency, we don't want to attach any resonance frequency. So we want all the motion source in the low side. That means a stiff, higher stiffness on the girder. Overall, we want the lower this transmissibility ratio. Different facility, they choose different low natural frequency, but overall the trend is we try to push this natural frequency high so that we can cover all those environment motion frequency in this low side that not touch the resonance frequency. And this table lists the different facility, how their lowest frequency and their transmission ratio. In light source 2, we get a very good performance. This really benefited from the via source elastic pad design. And in our machine, we can reach in the same girder, it is magnet-to-magnet motion control like 25 nanometer in vertical plane and horizontal plane about 150 nanometer. APSU, they are targeting to 10 nanometer, those uncorrelated motion. And for the girder-to-girder means span the whole ring, then we can achieve like 70 nanometer in vertical and 600 nanometer in horizontal. And in APS, their goal is to touch 20 nanometer performance. And the thermal stability from the girder, it is we want to minimize the temperature-induced distortion. So we here give an example. We use a via elastic pad. With this advantage, it can allow the girder movement relative to the floor, and also when the temperature changes, the girder can one end can expand without bend. This requires a tunnel area air temperature stability within 0.1 degree, and to avoid the girder thermal band. In our machine, 0.1 degree means like 4 nanometer magnet misalignment, and also the floor expansion due to the foundation changes or outdoor temperature changes. We can see it in the winter, between winter and summer. That can cause the girder deformation. In light source 2, we can control like 7 nanometer deformation. And other source like thermal stability that come from the outdoor temperature, tunnel air, cooling water, this electric rack, etc. They affect the girder, magnet, power supply, and BPM stability, then affect the beam orbit and feedback system. And then we can also improve the power supply stability. Magnet power supply stability directly affect the electron beam motion. For the dipole, it is a first order effect. So in light source 2, we have 15 ppm, and the new machine try to push 10 ppm. Quadruple and sectable power supply, they are high order effect, and in the new machine, they push to 10 ppm in the quadruple, and 50 to 100 ppm in the sectables. So this gives the example by doing the girder design optimization and control the power supply stability, how the machine performance looks like. The left side is from ESRF ring, and the right side is a new ring. And we can see that without feedback system, the old machine integral motion is 2 and 4 nanometer. And then with feedback on, it can suppress the motion down to 1 nanometer. In the new machine, without feedback, the beam motion already been down to 0.3, 0.4 micrometer. It's already better than the feedback on in the old machine. With feedback on, it can suppress the motion even further down to 200 nanometer. So how could we measure the mechanical motion? For the shorter term beam stability, in the tunnel we can use geophone or accelerometer. So this is example. At different location, we install the geophone and measure spectrum, and then we can see that in cell 26, there's a clear peak, 52 Hertz. This is from the water pump, we can track the source. For the long-term stability, it's basically drift between different sections or accelerate to the experimental flow. Example is SLS that choose positioning and a position monitor system. and can monitor and adjust the long-term drift. And in APSU, they implement the machine motion measurement system to monitor RF BPM and X BPM movement relative to the reference, and they can achieve like 10 nanometer resolution. This is planned to be used as part of the long-term drift correction. So the source propagation to the electron beam motion, it is basically produced by the mechanical motion of the magnet, which moves the center of the field and kicks the beam, or electronics noise in the magnet power supply to vibrate the magnet field, and also the BPM noise via the feedback system. This shows if there is a kick, how is a closed orbit distorted in the storage room, and they can express in this way at different locations. The amplitude will be different, depends on the source, and observe point, the phase advance and beta function, and also the tune of the storage room. So we express the relationship between the source and also beam motion with the response matrix, and then this is a connection between them. This is a principle and also foundation for the orbit feedback system and noise locator by using the inverse response matrix. In the orbit feedback system, we use a BPM reading and calculate the required correct strength and implement in the machine. And for the noise locator, instead of apply the correct strength, we can calculate the required correct strength and pinpoint the area which we need to apply the correction. So this is an example to show how we use noise propagation in the frequency domain. At every BPM, we have their spectrum, and we can see that there's a peak frequency at 60 Hertz, and then we pick this frequency and then amplitude, and doing the inverse response matrix, we can see that the required kick location is very clean in one location. This is basically pin to our finger point. When the high voltage is on, it can introduce 60 Hertz. So that's about the source perturbation and how does it propagate to the electron beam. Then next I'll talk about the diagnostic system that we can monitor the beam stability. So on Monday, Gonza gave an amazing talk about the review of the BPM drift compensation scheme. I will not go too much about BPM. Instead, I will highlight a few things here. So for the RF BPM, how the evolution looks like. So from earlier time, we have analog signal, and it takes seconds to get the whole orbit resolution, about 100 micron. In 1990s, start to have the digital signal, and that can provide slow kilohertz and turn-by-turn data. Resolution also improve to 30 micron in slow, and turn-by-turn data about 500 micrometer. And in 2000, there will start to appear combine digital and FPGA together, and then can put a much more larger data volume, and also the accuracy is much better. Resolution like long-term stability 3 micron, and similar for the turn-by-turn data. Now we have the faster speed and large memory, and also better stability. Give an example in light source 2. We have the 10 Hertz data, 10 kilohertz TBT, getting the BPM position, and also bunch by bunch beam position, and also intensity. The resolution, like in Libra, they can achieve like 100 nanometer stability. So this represents one example of modern BPMs, APSU, RF BPM button, and also the Libra brightness plus electronics. We can see that there have been tremendous progress on the BPM function and resolution improvement. So BPM resolution improvement basically every decade, it improved by 1 order from 100 micron to 100 nanometer range. And the electronics development also continue to improve the BPM resolution stability. We also have the larger data process speed and also large data size. The the design and improvement of the BPM come from both the in-house development, such as Sirius, Lysos 2, or Diamond 2. I see they are also developing in-house BPM and also commercial product in parallel. So this shows examples how we improve the BPM stability. In BPM stability, it is crucial because if the BPM resolution is 1 micron, you cannot correct the beam orbit better than 1 micron. So it has to be better than our orbit stability requirement, better than sub-micron. So from electronics, the efforts including high stable temperature rack control, plus minus 0.1 degree, and in ALS, they use a piloton control and improve the electronics stability within 0.2 micron. And also they have the RF switching, such as Libra Plus and Sirius. They can reach 50 nanometer stability. In Lysos 2, we are implementing ZBPM and also RF switch. This shows the improvement from current BPM to the new BPM. The stability can improve from 130 nanometer to 10 nanometer. And from mechanical, we can improve the high stable BPM support to isolate the ground motion, such as use INVA support or the granite to support the BPM. We can also use a mechanical motion monitor system to see the BPM mechanical movement. Another type of the diagnostic we use is a photon BPM, is to monitor the photon beam stability. It's usually located at the front end of the beam line, 10 to 100 meter away from the source. And these are the two examples, like the blade photon BPM or grid photon BPM. I saw Peter is also developed another type of BPM right after the front end, looking for that product. And those photons of the BPM, because it's far away from the source, so it's very sensitive to the beam angle stability. It can be 10 times or higher than the regular RF BPM. This is the most sensitive knobs to control the beam position at the beam lines. Photon BPM electronics, usually they are designed similar as RF BPM because it's easy to accommodate in the electron beam feedback system. The stability can be 0.2 micrometer long-term stability. However, it's mostly used for the hard X-ray, and it's also photon position or photon energy dependence. So it's difficult to use soft X-ray. And with the BPM data, what could we do? So this shows from the BPM system, we can have the ADC data, turn by turn, fast data, and 10 Hertz data. With 10 Hertz data, it has the X, Y, and intensity. We can track the beam long-term drift from seconds to days and see the low frequency spectrum. We can also use intensity for the precise beam lifetime measurement. For the 10 kilohertz data, we can do the short-term beam stability monitor from millisecond to seconds. We can do it a noise locator. We can use them for the faster feedback and also high frequency spectrum. We can see that this example in Lysos 2, we use a live beam motion spectrum. We identify the peak motion frequency and also amplitude that we integrate the motion at the operation time. They can easily track the daily machine performance. We also use the BPM turn-by-turn data to check the beam stability, beam dynamics study, injection transition, collective effect study, etc. So this is an example how we use BPM data to improve the beam performance from Soleil. They use a noise locator, which is used to pinpoint the motion source. And by knowing where the source is, we can improve from the source. So this is the spectrum. We can see the peak frequency. Then by using this peak frequency, they pinpoint to certain location and identify the peak at 46, 50 hertz, etc. And then localize the source from the cooling fan in the kicker, FCTs or shakers, and the strategy, like here, they move the cooling fan from one design to another And after this different improvement, the spectrum improved from blue to the red. This shows spectrum integral improved by a factor of 2 by changing the source noise. So that's about the diagnostic system, what signal it can do, and how we achieved it today. And next, I'm going to go to the feedback system to increase the beam stability. So some noise we can improve, some noise we cannot improve, or we cannot even control it. So feedback system is next level. We should use light source, mostly use a global orbit feedback system. By using the SVD algorithm, it uses slow corrector and faster corrector. Slow corrector, they are usually strong kick. It's a milli radius. However, it has a limited bandwidth from DC to a few hertz. For the faster corrector, it is a weaker kick, usually 10 microradius. It can correct a ratio by 10 kilohertz or to higher ratio now, and bandwidth limited to DC to a few hundred hertz. And here I show light source 2 fast feedback system as an example here. And this is a diagram of the fast RB feedback system. Electron beam has a motion, then BPM detected, and then cell controller process the BPM data, and then calculate the required corrector strength and send to the power supply controller, to the power supply, then go to the magnet to the chamber, then feedback to the electron beam. This shows the feedback system control design. We total have 30 cells. Each cell will have 3 faster corrector and 6 DC correctors. We also have 6 arc BPM along with a few ID BPM, depends on the ID location. And both of those systems can do the 10 kilohertz sampling rate. It is a FPGA-based parallel process for the cell controller and SDI link. Cell controller, it is used to receive the local BPM data, and SDI link is to transfer and receive the BPM data in the other cells. And also this FPGA carry out the FOFB calculation. They transfer the power supply data to the power supply controller. So overall, it has a high-speed calculation and a fast data delivery. With this system, we can achieve the faster correction cycling for the large bandwidth. And this illustrates how we do the algorithm control in the fast RB feedback system. So between the beam position and required kick angle, we can do inverse matrix, U sigma V matrix. However, we don't directly apply this correct strength. We add the factor of the Q here. Q here, it is used to control individual mode compensation and can change the gain. With this method, we can control each individual eigen mode with different controller and with different compensation in the frequency domain. The performance of the fast RB feedback, we use gain and bandwidth to characterize it. So high gain means we can suppress the noise smaller, and large bandwidth means how high the frequency is this fast RB feedback system can correct. This shows an example in light source 2 how we do the fast RB feedback to improve the gain and bandwidth. We did stage by stage. Latency characterized because this latency basically defines the feedback bandwidth and also affects the gain. From power supply, vacuum, etc., this part, the contribution of the latency is about 70 to 80 micron. And BPM in the old time, it's about 150 microns, larger than our expectation. Turns out because engineer, they put manually put a delay here. After we fix it, it improved to 15 to 20 micron second. And then to the cell controller, the delay, we found that the update ratio should be 10 kilohertz instead of 5 kilohertz. So this part also further improved the latency and overall the total latency is 220 micron. And this overall, so by doing this improvement, we overall can improve the bandwidth from 200 hertz, 50 hertz to 400 hertz in horizontal plane, and the vertical about 300 hertz. Also, we get the gain increase by 3 times, integral motion reduced by 30%. This shows ID BPM, the source beam stability with feedback on and off. So the horizontal beam motion is about 0.6% of the beam size, vertical about 7%. With fast RB feedback only, the corrected strength can accumulate in a week, usually about half of the full strength. However, if there are some big changes, this can push the fast correct to saturate. It also not sufficient to maintain the long-term beam stability because we only have 90 fast correct to target 200 plus BPM. So to solve this problem, we implement the unified RB feedback system, including ID and XBPM interact with a fast RB feedback system, and to reach long-term stability down to 1 micron. Usually slow and fast RB feedback system, they are not compatible in the common frequency range. And different machines use different methods to solve this problem. Nicholas gave a great summary, so I just take his slides here. One case is they use FOFB only, but they download the strength, which I showed here in red. When there's a DC component in the fast correct strength, they shift to the DC, shift the strength to the DC correctors and then implement in the machine. Another case is FOFB and SOFB. They interact with each other, the orbit communication between these two systems. So this I showed in black. When there is a residual orbit that cannot be fully corrected, and they use a slow correct strength, calculate slow correct strength. They don't do directly just apply the strength. They need to change the predict orbit change and change the fast orbit feedback reference. So this is the interaction. And Nicholas put both of those integrate together by using the interaction and download, combine all of them together, and that can achieve short-term and long-term stability at all the source points. This is the example to show Soleil achievement with FOFB only and combine both of them together. And taking his idea, we recently implemented this system in Light Source 2. We unify normal orbit operation feedback, slow, faster feedback, RF frequency feedback into one feedback system. We including knobs as a 180 DC corrector, 90 faster corrector, and RF frequency. We are targeting to 224 RF BPM and 3 X BPM. This system is very flexible to adjust the ID bump, binding magnet source bump, and also X BPM photon local bump at any times. This is what we achieved. Use FOFB only, and versus with unified orbit feedback only. We can see that with this new system, we can maintain the beam long-term stability very well at all beam lines, and they are very happy with this achievement. So that's about the noise or the source. We cannot, they are not reproducible, and we cannot predict. For some source that perturb the beam motion, that are reproducible, we can use a feed-forward method. So for the such as the ID gap change or the phase change, it can change the field integral and perturb both the electron beam and photon beam motion. So we can use ID correction coil or storage run correctors, and we can use storage run electron BPM that can achieve like a micrometer accuracy, and by compensation, makes the orbit distortion back. This is good for the electron beam stability, not transparent to the other. Now it's transparent to the other beam line, but it may miss the undulator steering on the photon beam, which beam line will see. So in SLS, they include in the beam line photon BPM in this correction algorithm, and they can correct the ID source position and angle. better to sub-micron radius photon beam stability. So we correct the electron beams side motion mostly. Now, beamline side, they have their optics, and some of the beamline, they implement the active beamline component feedback. This shows an example from HEX. They have two feedback, one is slow, one is faster feedback system by using the beamline knobs, including the monocrystal, pitch, and roll. They can run up to 100 Hertz. They can also use a mirror pitch to then up to 5 Hertz because it's a mechanical motion. Then they target to the diamond BPM in the beamline. By combining those two systems together, they can reach the high photon beam position and intensity stability. This shows feedback off and feedback on, how the beam stability performance looks like. Note that this is a very different scale. This is 5 times larger than this plot. So this shows a great improvement on the beamline performance. However, this system has a limited bandwidth because it uses optics component, and then that limits the correction bandwidth. And recently, Diamond, they developed a new method, use feedback system by using the X-ray BPM, but use a control electron beam to keep the beam stability. This system will correct both the photon motion from the electron beam and also beamline optics. They use a storage 4 fast corrector and build the transparent bump, not leak to the other area. That's always debating whether we should correct the beamline, their motion carry out to the storage room. By using this local bump, they can limit this correction to the local only. And then this system, this is what they have achieved with feedback off and feedback on. Overall, they can maintain X BPM stability within 3% of the beam size, and the bandwidth can be larger than 1 kilohertz. So this is a great example how we can carry forward to integrate the beamline feedback system. And this lists the feedback system status in different light source. Thank you to everyone's input and contribution. Basically, majority of the feedback system, they use slow and faster system together, and BPM sampling rate to 10 kilohertz or even higher, and this will help to improve the bandwidth. Another notable result is that, the new machine, such as Max4 or the EBS machine, because it's very carefully designed with better performance from the design stage. Without feedback system, they can already achieve like a few % of the beam size. With feedback system, it can further improve. So towards the future, we want to have the better angle and stability performance. So it is important to feedback on the beamline component because with the electron BPM, we have a limited resolution, and then the mechanical thermal instability source relative to the ground motion between experimental flow and X-ray flow, they are always this long-term drift. Another limitation from the ground motion, we call the Atl Law. So this is a basic relative motion between 2 points and separated by distance and a certain time. This always causes a long-term photon source drift relative to the source. And in APS, they are proposing to use a unified electron and photon feedback system and to stabilize beam at the sample. This has been advocated by Bob Hattel many years ago. This illustrates how the communicate the signal together, use a unified RB feedback system. And in this slides, it shows APSU, how do they achieve, a smaller beam size and divergence with a larger bandwidth. So to reach the larger bandwidth, they minimize whole feedback system latency. By pushing the BPM to the high sampling rate, they use turn-by-turn data, which is 270 kilohertz. They use a faster corrector and sampling rate like in our case, 10 kilohertz, they are 22 kilohertz, and also make the bandwidth up to 10 kilohertz if they want to push the full feedback system down to 1 kilohertz. And also they control the overall system, the process latency to 44 micron. Remember that in light source 2, what we achieved now is 220 microsecond, just to give you a comparison. They also use unified orbit feedback algorithm. Basically, they combine slow and fast corrector without compromise the spatial and dynamics performance. And then in APS, they have demonstrated this whole system in the part of the 2 sectors. And this shows the spectrum improvement in horizontal and vertical plane. And they achieve 1 kilohertz bandwidth. So at this point, I'm closing to my work and also in the future outlook. The new synchronized source, basically we are really approaching the diffraction limit emittance. Emittance change by 2 order or higher magnitude. This will push the smaller beam size. And this also gives a tight tolerance on the beam spatial and time domain stability from the high performance beamline. Otherwise, the improvement try to get the better resolution will not be able to reach. And our community invented and continue to develop the different means and method to advance the beam stability, including investing in the facility construction in the earlier stage and reduce the environment noise source, or improve the stability of accelerated component, such as BPM, resolution and stability, power supply stability and control. We also advance in the feedback system towards the future. We are looking forward to the unified orbit feedback system. It is a trend to stabilize both electron beam and photon BPM in a large bandwidth. So that's about my talk. These are the reference I've been learned from this whole subject. Thank you, everyone.
Thank you, Guimei. Any questions from the audience? Up here. Oh, sorry, there's one in the front here. Yep, sure, go ahead.
Hi. You mentioned that I think at APS they have a hydrostatic leveling system between the electron BPMs and the front-end X BPMs. Is that something that's rolled out on all of the front ends, or is that a one-off test? Could you elaborate a bit more on it?
Oh, you mean this one, right? So in this system, I would say it really depends on the beam lines. As I say, the photon BPM really depends on the photon beam BPM availability. Like in light source 2, we cannot really have the X BPM available in soft X-ray beamline. In this case, we cannot integrate the X BPM in the feedback system. In APS, it's different. Their storage are 6 GeV, and their beamline, I would say mostly it's hard X-ray beamline, but I'm not sure. I hope someone from APS can address how their X BPM looks like, and as long as it's available, then it can be integrated into the feedback system. Yeah, my comment about the X BPM integrated into the feedback system, most risk is if it's BPMs from beamline, especially there is optics in B10, then those optics can introduce error and mess up the X BPM performance. Then the feedback system will be in not the right state. So that's a concern in our machine. We mostly integrate into the front end X BPM, which are very reliable because we know there's no optics in B10, but integrate to the beamline X BPM, we also always have the concern the beamline optics can make the X BPM data not so reliable. So towards the future, I would say this will be challenges, and also have to have the mutual agreement between accelerator and beamline, whether we can reliably integrate the XBPM in the feedback system.
I was thinking about you mentioned there's a hydrostatic leveling system.
Oh, okay.
Monitoring between the two, and I was interested if that was everywhere or just a one-off test to see if it worked.
Okay, yeah, a very good question. So I did communicate with them. In the initial stage, they will use this system in the monitoring system, but in the long term, they did want to implement it in the whole system. And yes, that's a status where they are now.
Okay, thanks.
Thank you.
Gumei, thank you for this nice overview. I just wonder, are you going to do modeling of the system using transfer functions, measure it or maybe calculate it?
Which transfer function, sorry?
Of the elements?
Oh, use SRW?
No, this is, it was some work going on already at the NSLS2 with Timur. They were trying to use, transfer functions of the elements and really figure out how the feedback will work, so to model it.
Right, yeah. Soko did more work with hex beamline. Now he graduates. I hope this work can be continued. It is very helpful, by using the model between different source points, such as we use ID source as a point to simulate the noise position, and then to the beamline optics as another source point. It's equivalent as a storage and correction system. You have the corrector at different location, then they will have different response metrics. Then this will help to, if the beamline sees the motion, they can use this response metrics to inverse and pinpoint the noise locator instead of, electron beam motion and beamline optics mixed together. We cannot quickly identify which one is real source. So this transfer metrics from different elements will be very useful to help diagnose the problem.
Thank you. Great. It's still going on.
Sorry, time for just one more question here right in the front.
Okay.
Yep.
And could you go back to page 23, which is about photon BPM?
Sorry. I think
about long-term stability.
Okay.
This page shows 0.2 nanometer is long-term stability.
20.
If 0.2 micron,
Hold
it will 23.
Oops, sorry, I'm in the wrong direction. 22, I
This is
guess.
23.
Oh, 23?
Yes.
This one? Sorry, oh yeah, this is a type of error. Definitely it's 0.2 micron.
Okay, now
yeah,
I see.
Sorry. Yeah,
That's it.
yeah, thank you.
Okay, unfortunately, that's all the time we have, but thank you so
you.
much for a wonderful talk.
Thank
and we
you.
can thank Gu Meng again. Okay, so now we're going to welcome Janis Brolin. He received a diploma in 2011 from Hamburg University with a thesis titled Commissioning of Electro-Optic Electron Bunch Length Monitoring at Flash. Between 2011 and 2016, he did PhD studies at Lund University and Max IV Laboratory. In 2016, he was awarded a doctorate of philosophy in accelerator physics with a thesis titled Emittance Related Topic for Fourth Generation Storage Ring Light Sources. In 2017, he was a postdoctoral research fellow at CERN in the beam diagnostic group, where he studied linear and nonlinear optics to optimize the final focus systems for the click linear collider collaboration. Since 2019, Janis has been the Stability Task Force Coordinator at Max IV and Lund University. Today, Janis is going to talk to us about beam stability in the Max IV 3 GeV storage ring. Take it away.
Yeah, thank you for the nice introduction. And thank you for giving me the opportunity to talk here to you. Today I'll present beam stability at our 3GV storage ring light source in Sweden, and I'll be talking on behalf of the entire MAX4 team, actually. The outline, I'll quickly introduce this idea of the MAX4 Stability Task Force, and I'll then talk a bit about mechanical vibration, mechanical stability at our lab. I'll go into some figures for electron beam stability in our 3GV ring, and I'll also talk about some diagnostics on the photon beam stability we are doing. So the MAX4 Stability Task Force is a multidisciplinary and cross-divisional task force. It's working towards the goal of delivering stable photon beams. And already during the design phase of our facility, this task force is active and, for example, came up with a mechanical stability philosophy based on mostly passive stability. For example, one way to do that was to try and maintain the very good green field ground vibration levels that we have at our site, 20 to 30 nanometer RMS. And then going through a lot of things we heard in the previous talk, right? Frequency isolation of sources, careful design of support structures, for example, instead of using magnets on girders, we have this magnet block design. You'll maybe see it tomorrow at the Solaris visit as well. Until 2019, Brian Jensen was coordinating the Stability Task Force and did a really great job there. So now MAX4 is a facility in user operation, so we're having 16 beam lines taking light, and a few new tasks came up, for example, improvement of operational routines at the lab. Also, communication, being a contact person to beamline staff in case of some sort of unstable beam. We're doing measurement, monitoring of many stability-related parameters. I mean, obviously, position of photon beam, electron beam directly, but also mechanical, electrical properties. Sometimes even helping in the development and commissioning of relevant diagnostics. So when we started with MAX4, we were on a green field. We were basically the only building around. Let's see how that works. How am I pointing at this? Oh yeah. So you can see the circular building here hosting the 3GV ring. Was basically the only building in the area, besides maybe from our neighbors of the European spallation source you see in the top right. And since then, plans were coming into life that the municipality, Lunds Commune, will develop a whole new district of town around us. So everything that you see here in gray is buildings, structures to be built. So that's also residential areas. There might be highway exit, there might even be rails for high-speed trains to Stockholm. There's even ideas about extending our 3GV LINAC to a soft X-ray FEL, so that's in a CDR stage. So there's a lot ongoing, and we need to work on it to actually maintain the floor stability levels that we had and that we have so far. And I'll come back to a certain concern about speed bumps in connection with heavy traffic in a moment. One main source of outside vibration on the floor we cannot really complain about because it was there first is the E22 highway, and we've done a little survey there. So we had the Swedish road authorities counting heavy vehicles, so that's the blue curve in the upper plot here. And at the same time, we evaluated on the experimental floor just high peaks of ground vibration, and we plotted them together, and that's a quite nice match. So this E22 is a main source of floor vibration at our lab, but nevertheless we reach quite low vibration levels at night. So the lower left plot here is done for a beamline quite close to this E22 road, so going almost down to 2 nanometer RMS vibration overnight, and then increasing maybe up to 7 or 8 during the day when most heavy traffic is on the way. We are monitoring a lot of these values, floor vibration, for example. There's a lot you can find once you look. I mean, the obvious, not sure, is the low frequency during daytime, but there are also other things that you might not expect and that you only find once you're looking at monitoring. I mentioned this combination of road bumps and heavy vehicle traffic, for example, delivering to construction sites. So that was a big concern, so big that we actually conducted a little test here. So you see 3 vehicles of different weight, and maybe you also see a temporary road bump just hiding here behind the white vehicle. And all of that at a distance of around 120 meters to our storage ring. And looking for vibrations induced by these trucks passing over, and yeah, it could be getting severe if you look on the very right in this plot here. So if a heavy truck does that at 40 kilometers per hour, this might add to our stability budget that we don't want to do. We're doing these tests so that we can early communicate to the municipality and give suggestions to certain radii in which such road bumps might be installed or not. Similar procedure a few years back, the tram tracks at a similar distance to the lab, where we were able to introduce insulation in the tram tracks and also speed limits, so we don't have any added vibration from the tram. Yeah, quick one here on vibration, isolation policies, isolation of internal sources. There's a new cooling unit at a beamline, and immediately you get some peaks here in the spectrum, which were then able to be traced back to that cooling unit. And of course the springs for isolation were missing. So, I mean, there are policies, but somebody has to go around, and my colleagues do that very well, going around, see that these policies are followed. Coming to some 3GV electron beam stability. Should say the limits to everyday delivered beam stability are mostly of operational nature. So, I mean, there are malfunctions of systems not directly related to the orbit feedback or to feed forwards, but could be a lot of things. It doesn't have to be an actual malfunction. It could be a bad configuration of systems. So that's usually what limits our delivered beam stability. But under typical condition, when everything works, stability is quite good. Put the figures in here. So this is the integrated RMS displacement, and we are well below a 10% limit here. This is data taken for RF BPMs that are flanking the long straights where we have IDs positioned. We don't need a fast orbit feedback to reach that goal. You see the difference between only a slow orbit feedback running, that's the dashed lines here in the plot, and the fast orbit feedback is quite good, not too impressive yet. We have a bandwidth of the fast orbit feedback of around 50 hertz, simply because not so much study time has gone into full development of this system. but the fast orbit feedback system has already an important role in our lab, and that is to compensate for induced transients induced by IDs that are moving mostly close to minimum gap. And a slide here by Magnus Sjöström shows basically how if a Wiggler insertion device is closing the gap, let's start here on this side, without the fast orbit feedback system running, we get quite some distortion on the orbit, visible to all beam lines. But with the slow orbit feedback and fast orbit feedback systems both running, these transients can be fully eliminated, and that's already at a quite conservative 30 Hertz bandwidth back then. So that would be our main purpose of the fast orbit feedback at this point. And I should also draw your attention to actually 2 contributions on this conference that are dealing with various feedback and feed-forward systems on beam and optics that we're having at the lab. Coming to our photon diagnostics in the front end. So in each of our beamline front ends in the 3GV ring, we have a set of 2 XBPMs installed, an upstream and downstream one, and they work based on tungsten blades and an X-shape geometry. And well, they can be calibrated with motors on absolute encoders. And we have readout electronics, a so-called ALBA electrometers. We are considering a change to a different system, a Libera photon system that would, for example, have the benefit of getting the data we are taking with the XBPMs closer to the data we are already having from the RF BPMs, because that's a Libera Brilliance Plus system. But yeah, today available for measurements are 10 pairs of XBPMs, 10 beamlines, and the system is set up for the moment to do long-term monitoring of the X-ray positions in the front end. So we're having a readout rate of 1 Hertz, and we're continuously monitoring, archiving these beam positions. And yeah, every now and then this has already been a helpful tool tracking down issues that beamlines had on their side. Also combined with, for example, comparing spectra of electron and photon beam motions and the spectra that a beamline would see on their detector. There are a few issues we are still having with this system. You can see here I'm indicating where we have a current drop of 20 milliamps. There is quite a strong dependence of the photon beam position on the stored beam current that shouldn't really be there. So this is something we are constantly seeing in every top-up. But apart from that, we can also get a grip on drifts, measuring drifts with these XBPM system. Of course, the big question is then, what is drifting there? Is it on the electron beam side? Is it mechanical? Is it temporal drift? Is it sitting only in the XBPM itself? So there are still a few things to investigate around the system, but well, it didn't keep us from trying a proof of principle experiment using the XBPMs in an orbit feedback. I'm calling this XOFB here at max 4. So what I'm doing is basically correcting angle and position in both planes in an ID straight. And for that I'm taking the data from the upstream and the downstream XBPM. And I'm then evaluating, averaging to some extent, and I'm updating the slow orbit feedback reference value, something every 10 seconds. And that's fast enough to take care of slow drifts. So typical delivery condition, 300 milliamps, 10-minute top-up intervals. And you can see here the time when this prototype of a feedback is running, we are successfully compensating drifts as expected. We see, as I mentioned, variations in the beam position measured by the XBPMs when current drops. So that are the spikes that you see here, which would, if the feedback is not running, be sawtooth patterns. So that's something to work on. Nevertheless, as a proof of principle, this works, and it would be a tool, for example, to compensate drifts and to bring the beam stability evaluation closer to the beam line by moving it into the front end instead of validating it only with the electron beam surrounding the ID. So I'm waiting for some good moment and beam study time, and I can actually do a test with the scientific beamline, because they are the ones who should, in the end, tell whether we do an improvement to the delivered photon beam stability. So I'm coming to my conclusions here. So the efforts during the design and construction phase have really paid out. So we have a 3 GV storage ring light source with a very good passive stability. Now it's time to make sure we maintain that stability while a lot of things are happening and are built around us. Well, I mentioned the point of increasing importance for a typical light source going into operation, and continuous monitoring of beam stability parameters is important. Quick reaction when there are deviations, and of course close communications to the beamline staff, but we don't want to be told by the beamlines that something is wrong. We want to find it out first. That's at least my opinion. Then there's the extension of, I call it machine-owned diagnostics on the photon beam in the front end. So XBPMs on the photons. In the front ends, we need a little bit better understanding of the signals we are measuring. I mentioned considerations changing readout electronics here. And I should also mention there was a poster on Monday on this conference about even a novel design of an XBPM head that might be of interest. Yeah. And with that, I would like to thank you for your attention.
So it's, I'm wondering, do you do the photon XBPM calibration, like the current dependence or the ID photon energy cost, the photon energy dependence?
Yeah. First of all, I think what I'm showing here is.
It looks a strong dependence. Will you have a plan to do this calibration so that you know with beam current change or the photon energy change, then those XBPM will be reliable to read the beam position?
I mean, one thing is, of course, calibrating for different ID gaps and calibrating for the different distributions of photons, and that is necessary. But to my understanding, it shouldn't be necessary to calibrate for different stored beam currents in the ring. So I'm suspecting there's a malfunction somewhere on the path between the BPM head, cables, the readout electronics. I hope we don't have to calibrate for different beam currents. Mm. Yeah. We are monitoring with seismometers. We also have a few vibrometers, other means of mechanical vibration, apart from temperature and also humidity. So we're actually working on a sort of a project where we have many rather cheap available sensors for mechanical vibration that we can just spread around everywhere and get as much input as possible there and feed that into the archiver that already contains a lot of information on electron beam positions, photon beam positions as well. Yeah.
Awesome, perfect. Thank you very much.
Yeah, you're welcome.
Okay, if there are no other questions, sorry, we've got one. Go ahead.
Jonas, thank you for a very nice talk. I have a question about temperature stability. You just said you have many monitors, and I think the temperature stabilization concept at X4 is rather different from other light sources. In fact, I believe there is no active air conditioning. So what's the temperature stability you have recorded over a year?
Yeah. That's right. It's in the accelerator tunnel. This is also a passive temperature stabilization that just finds its equilibrium with the dissipated heat from the equipment. That's also why after a shutdown where many concrete doors were opened, we need on the order of 5 weeks to get back to our usual temperature. Variations of temperature, I would have to come back to you to get really the exact value.
Thank you.
Mm-hmm.
Okay, we're running a little bit behind schedule, so I'm going to thank Jonas again. A wonderful talk.
Thank you.
Okay, so now we are going to invite Mitsuhiro Misaki to the stage. Okay, Mitsubishi joined the Japan Synchrotron Radiation Institute in 1995. He was involved in the construction and commissioning of the Spring 8 storage ring. After commissioning of the Spring 8 storage ring, Mitsuhiro was engaged in the research and development of mainly non-destructive beam diagnostic techniques using synchrotron and undulator radiation. Most recently, he has worked on the Spring 8 storage ring upgrade and the next generation synchrotron light source, Nano Terasu, in Tohoku, focusing on the development of BPM electrodes, beam impedance estimation for the vacuum chambers, and a bunch-by-bunch feedback system to suppress beam instability. So today, Mitsuhiro will be talking about adaptive feed-forward control of closed orbit distortion caused by fast helicity switching undulators.
Thank you. Thank you for the introduction and giving me this presentation opportunity. I'm here to talk about a new COD correction scheme based on adaptive feed-forward control. This is presentation outline. After a brief introduction, I'll first explain the helicity switching undulators of Spring 8, and then I'll explain the details of adaptive feed-forward control AFC. Okay. Next, I'll discuss why did not choose fast global orbit feedback. Finally, conclusion. Storage ring-based light sources are now essential platforms for photosciences and related applications, including industrial purposes. Development of the next generation light source in progress around the world. One of the important figures of merit for light source users is brightness of light. It's related to the degree of transverse coherence. However, high beam stability is essential for successful developments. In modern and future light sources, to achieve the inherent light source performance, the Poynting stability should be significantly smaller than the electron beam size. The fourth generation light source link will essentially demand ultimate orbit stabilization. One of the most important issues is how to suppress orbit disturbances like this in a ring. There is various error sources causing beam orbit disturbances in the storage ring. For example, mechanical motions of magnets or vacuum chambers due to ground motion or cooling water and so on. Or electromagnetic noises of magnetic power supplies or other sources. And coming from insertion devices, for example, magnet pole gap or phase motions, polarization switching kickers. How to cure the orbit disturbances? There are three main methods: feedback and feed-forward controls, or removal of error source itself. Global orbit feedback is widely used, and it's very effective for the case the error sources are unknown. There is a slow COD correction below 1 Hz. There is not only slow COD correction below 1 Hz, but also fast feedback system with frequency bandwidth up to typically 1 kHz. On the other hand, for the case the error sources are known, an ideal solution is removal of the error sources, but it may not be feasible for all error sources. In this case, feed-forward correction is often used. Feed-forward counters are located near the error sources without removing the error source itself. For example, due to the orbit correction, due to ID motions, fast switching oscillators is applied. If the error source conditions is slowly changing, we need to dynamically update the feed-forward tables to meet the changes. This is what's called adaptive feed-forward. This method is applied to the orbit disturbances, applied to suppress orbit disturbances due to the switching oscillators of spring rate. The healthy switching oscillators of spring rate ID23 and ID25, this type of oscillator is used for photon helicity switching in X-ray magnetic dichroism experiments. This is twin helical oscillator system, which consists of two helical oscillators for right and left-handed polarization. They are placed in tandem. Both polarizations are alternately switched by dynamical horizontal orbit bumps A and B. The repetition frequency of the switching is 1 Hz or 0.1 Hz. When switching to the orbit bump A, like this, right polarization component propagate horizontally off axis and stopped at front end absorber in B brane, while left polarization right reached the experimental station. On the other hand, switching to the orbit bump B like this, makes reverse the situation. Right polarization, right reached the experimental station. Imperfect closure of these orbit bumps by Kicker error resulting fast orbit disturbances outside the ID sections. So to correct the orbit disturbances, two fast feed-forward correctors are placed at both ends. However, feed-forward correction accuracy gradually degraded with time, typically a few weeks. But so the deterioration rate is slow. For example, as shown in figure, the periodic orbit variation synchronized with the Kicker excitation was observed, including fast frequency of several tens of hertz. The oscillation amplitude typically several microns, which is detrimental to user experiments. The cause of the deterioration remains unclear despite having been investigated painstakingly by ID team. The feed-forward tables used to be updated a few times a year during accelerator beam tuning time, but it not be done timely user time. So this led to the need for a new correction scheme, AFC. So let's move on to the adaptive feed-forward control. Our goal for orbit stabilization is to keep the COD fluctuation below 1 micron even during the healthy switching. There are 4 key points to well-function the AFC. Automatic table updating without stopping the healthy switching. In other words, the table updating doesn't disturb any user experiments. And high precision and efficient extraction of the only error kicks coming from the switching undulators. And even if simultaneous switching of the two twin helical undulators, ID23 and ID25, were resolving each counter kick, resistant to orbit preservation due to error sources other than the twin helical undulators. Correction scheme. As characteristics of the COD variation due to the switching kicker, periodic variation with the switching repetition frequency of 1 Hz over 0.1 Hz, and containing fast components up to several tens of Hertz. But it's sufficiently slow compared with radiation damping time of millisecond order. So it can be expressed with superposition of instantaneous CODs caused by time-dependent multiple error kicks. As this equation, horizontal orbit displacement at BPM is expressed by multiplying the error kick vector by response matrix between the error source and BPMs. Feed-forward correctors are placed near the error sources. The relation between the counter kicks and the orbit displacement at BPM is expressed by this equation, which is an opposite sign of the previous equation. The counter kicks at the correctors are solved with the singular value decomposition method. In case of spring 8, there are 2 correctors for each switching undulators and 4 BPMs to detect the horizontal COD perturbations. For horizontal counter kick have to be well resolved, even while ID23 and ID25 are switching at the same frequency. The placement of BPMs and their noise reduction is very important. The selected 4 BPM sensitive to horizontal kicks at twin helical annulators. This is measured 4x4 horizontal response matrix between the 4 BPMs and 4 collectors. This is system overview. First feed-forward collectors are air core coils at the both ends of each of the 2 twin helical annulators. First BPM's readout circuit is micro TCA.4 based with 10 kHz sampling rate by fast acquisition mode. VME system for ID23 and ID45 generates the kicker and collector patterns along with each trigger signals. To synchronize the BPM data with kicker driving, the kicker trigger signals are fed to micro TCA.4 digitizer board. The synchronization is done by marking with the common timestamps of the BPM data and trigger signals shared on the control network. The correction pattern is updated by adding counter patterns obtained from the BPM to the previous pattern. The counter kick calculation and experimental verifications to achieve orbit correction accuracy of less than 1 micron, counter kick error of the first collector need to be within 0.05 micron. The important thing is BPM data processing. That is random noise reduction to secure sub-micron resolution and filtering to eliminate contamination due to error kicks other than twin helical annulators. For low noise extraction of the periodic COD variation, BPM raw data is acquired for several tens of periods. Figures shows an example of the FFT spectrum of low BPM data for 60 periods on 1 Hz switching. For holding process in the frequency domain, we picked up peaks at the repetition frequency and its harmonics in the FFT spectrum. You can see the red circles. After the low pass filtering, return to time domain pattern by an inverse FFT using the only picked up peaks. By this process, we can obtain the noise reduced one cycle time profile for periodic COD variations. There are one more important thing. To accurate counter errors, it's important to compensate the time response of the AFC correction loop itself. Correction loop in the frequency domain is shown in this block diagram. The transfer function from error kick to detected COD. Its amplitude corresponds to the response matrix. The phase part phi reflects the phase delay of the AFC system itself. In the counter kick calculation, inverse response matrix is applied to the detected COD. the phase delay should be compensated. In other words, the counter kick vector should be an opposite sign of error kick vector. If the phase delay compensation is not adequate, the error kick are not reliably counteracted. In the worst case, it even builds up. We measure the phase delay using a step function of BPMs by analyzing the step response of BPM. By analyzing the measured step response in the frequency domain, we can obtain the phase delay as a function of frequency. For phase compensation in advance, the measured phase delay was incorporated into the filtering process of BPM in the frequency domain. The complex low filtering for the FFT spectrum of BPM data filter phase function to compensate the time response of AFC system is an opposite sign of the measured phase delay. It's shown as a blue line here. To cut off high frequency noise, filter amplitude is fifth order Butterworth filter with 100 Hz cut off. It's shown as a red line here. So noise level of these processed BPM data reached 0.2 micron RMS. So we show the case of ID23 and ID25 simultaneously switching. The 4 counter kicks were solved with the SVD method. There are 4 modes, the singular values of 4 mode and the RMS CODs of each mode in random kick of 0.1 micron at each collector are listed here. The mode 1 and 2 with large value of large singular value are main component. So they apparently need to be corrected. The mode 3 and 4 have significantly smaller contributions. Solution using only main modes 1 and 2 is inappropriate in kick angle and sign, so it's no good. The case using all 4 modes, the counter kick errors from the BPM is 0.1 micron, which doesn't satisfy the target correction kick accuracy. So it's also no good. The case correcting 3 modes, 1, 2, 3, excepting number 4 mode, correct counter kick errors is 0.05 micron, which satisfies the target correction accuracy. So we adopt the counter kick calculation using the 3 modes discarding mode 4. This is experimental verification of simultaneous 1 Hz switching on ID23 and 25. Before applying the AFC, observed orbit displacement at 4 BPMs is 20 to 40 micron peak to peak, like as shown in blue line. After applying the AFC, the orbit fluctuation drastically damped the same level without the switching. This red line shows as shown here. To confirm long-term performance, we adopt the AFC to ID23 1 Hz solo switching during user time operation. Without the AFC, the orbit fluctuation gradually grew at a rate of typically 80 nanometer per day, The red circle shows this growing trend. On the other hand, with the continuous AFC, it's kept successfully suppressed within 1 micron RMS over the long time, like this. So we discuss why did not choose fast orbit feedback FOFB. FOFB is based on a global correction scheme for fast orbit variations. As characteristics of global correction, its advantage is no need to identify the source errors. However, correction accuracy is limited by number and placement of BPMs and correctors. There are a potential risk of unwanted orbit distortions around the error source because the correctors are not always placed near the error sources. We show an example of simulation assuming the spring-8 staging, that is corrector number dependence of the global correction accuracy. As simulation conditions, the error source was assumed to be a horizontal single kick of 1 micron rad. We simulate the COD correction accuracy for changing the number of correctors placed with equal spacing. Small number of correctors results in unwanted orbit bump around the kicks like this. You can see 15 corrector case or 29 corrector case or 72 corrector case. This is unwanted local bump. Only the case of 144 correctors, this blue line shows that such a local bump doesn't almost appear. In this case, the distance between adjacent correctors are about 10 meters. So therefore, the correctors exist near single kick within a few meters. So conclusion, a new COD correction scheme with adaptive feed-forward control. The development and verification have been successfully done at spring-8. The AFC works well for suppressing fast periodic orbit fluctuation during operation of helicity switching undulators with kickers. It keeps the COD fluctuation suppressed with submicron order for a long time. Toward ultimate photon beam stability for next generation light sources, relying solely on global correction scheme, including FOFB, is not sufficient. When the error source is known, for example, such as an insertion device, a source suppression scheme such as AFC can be very effective. At least 2 correctors upstream and downstream near the error source would be sufficient not to leak the orbit distortions outside the ID sections. Both schemes in complementary relationship are indispensable to achieve the ultimate pointing stability of photon beams. That's all. Thank you for your attention.
Thank you for a very interesting talk. Do we have any questions? Okay, I don't see any. I actually have a couple for you, but I'm going to take them offline just because we're already running a little bit late. Sorry. I'll catch you after the session for the questions. Okay? Okay, let's thank... Okay, so now we're going to invite Pedro Baetra to the stage. So Pedro is an electrical engineer with a master's degree in embedded systems engineering from the University of Freiburg in Germany. His master thesis title was Design and Comparison of Hardware Architectures for Accelerating the Inference Core of Tree-Based Classification Ensembles, an FPGA experience. After working in the automotive industry in Brazil, he worked as a research assistant in Freiburg, Germany, in the field of ASIS and FPGA design to accelerate AI and machine learning systems. Since 2020, Pedro has been working with the Paul Schreier Institute on the design and measurement of feedback systems based on the RF system on chip for the Swiss light source upgrade. Today, Pedro will be talking about RF systems on chip for multi-bunch and filling pattern feedbacks.
So thank you for the introduction, and thank you the organizers for the opportunity of presenting our work. So today I'm going to talk about the evaluation of the IF system on chip for implementing the multi-bunch feedback and filling pattern feedback at SLS. So the Swiss light source is a storage ring at PSI in Switzerland, and it's in user operation since 2001. And PSI plans an upgrade for the storage ring, the SLS2 project. So the project consists in the replacement of the current storage ring for a new low emittance ring, providing up to 60-fold higher brightness for hard X-rays. And in addition to that, also the modernization of aging systems, including the electronics, not only electronics, but the complete system of multi-bunch feedback and filling pattern feedback. And in this context, we have been evaluating the Xilinx IF SoC as a platform for these feedback systems. So, and the first bean of SLS2 is planned for 2025. So the multi-bunch feedback main purpose is to stabilize the bean and avoid bean loss due to couple bunch instabilities. And at SLS, the system is also used to find other sources of instabilities and also to characterize the bean. The filling pattern feedback has been used to measure the charge in each RF bucket and with this information control the injection time, adjusting the charge per bunch given a user-defined pattern, and we call it a PSI filling pattern. So, and why the IF system on chip? So the system on chip integrates in a single device multiple CPU cores, ARM processors, a resourceful FPGA fabric, and multi-giga samples per second data converters, ADCs and DACs, and also various data storage and communication interfaces. And most importantly, for fast feedbacks, so it has a very low latency between ADC to DAC. So running the data converters at 4 gigahertz, 4 gigasamples per second, we achieved 120 nanoseconds for the latency. Yeah, so and for the evaluation of the IF system on chip, you have used the ZCU111 kit from Xilinx. So it features the first generation of the IF system on chip and also peripherals for interfacing with the chip. So we have reference clock inputs, which we can get the machine clock, the IF main clock of the machine, so around 500 megahertz, and synchronize the data converters and the programmable logic to this clock. We have Ethernet, such that we can communicate with the control system. And in addition to that, an add-on card that breaks down the ADC and DAC inputs and outputs, routing them to SMA connectors. So this is the high-level diagram of the hardware setup for testing the multi-bunch feedback and the filling pattern feedback at the SLS. So we connect the four bottom BPM to our RF hybrid network, such that we generate the sum signal and the different signals, X and Y. And then we use the RF SoC to sample the positional signals and to process them. So then we use the DACs of the RF SoC drive amplifiers, which then drive the kicker magnets of the multi-bunch feedback. So yeah, the firmware, so you have a unique firmware implementing the 3 dimensions of the multi-bunch feedback and the charge measurement or filling pattern measurement. So the ADCs of the multi-bunch feedback run, ADCs and DACs of the multi-bunch feedback run 8 times the machine frequency, approximately 4 gigasamples per second. And the filling pattern ADCs run at a slightly different ADC clock to acquire fractional number of samples per turn, such that we can implement an interleaving scheme to increase the effective sample rate of the ADCs. So here we see a one-dimensional diagram of the firmware of the multi-bunch feedback. So we sample the position signals at 4 gigasamples per second, which represent 8 samples per bunch. And for now, we just process 1 out of 8 samples, and this data stream goes through digital filters, and these digital filters generate the correction signals, and the user can decide when to kick the bean with a granularity of 250 picoseconds for now. And all the system is controlled by the user via EPIC's IOC running at the ARM cores of the IF system on chip. And here we also implemented as our user interface in Python so that we can configure the filter coefficients. We can monitor the ADC and the DAC data for every dimension of the feedback. So yeah, and for the filling pattern feedback or bunch charge measurement and arrival time measurement, so the firmware consists only in the acquisition of the data, and we acquire with one channel the revolution clock, and the other channel we get the sum signal. And so then a software running in a PC reads the data from the IOC and process it offline for now. Yeah, so the revolution clock is used for the bunch indexing. So the rising edge of the revolution clock is used to determine, so the first bunch after the rising edge of the revolution clock, we call it bunch number 0, and the last one before the next rising edge of the revolution clock is the last bunch, the bunch 479. So we have 480 bunches in the machine. So yeah, and the sum signal is used for calculation of the bunch charge and arrival time. And what we do right now, we take a bunch window of 200 seconds, and the charge is the area between the negative poles and the dynamic baseline, and the bunch arrival time is the time that divides this area in 2 equal halves, or this is an estimate for the bunch arrival time. So, and these algorithms are implemented for now in offline, so in Python. So, and the first results for the multi-bunch feedback, so we verified the function of the system, of the firmware, with simulation tools, so Vivado, and the firmware is implementing what we expect, and then we also tested the hardware system in a hardware in loop setup where we feed a arbitrary waveform to the system, and we measure the output of the DACs, and we compare it with a Python model. And on the right side, you can see the red curve is the hardware response, and the blue curve is the expected response, and you can see also in the black curve a absolute error. And this error is not because of functional problems of the algorithm, but rather so some imperfections on the hardware test setup. So we have some attenuation in the path from DAC to the other ADC, and also with the timing when comparing the waveforms. So yeah, and for the bunch charge measurement, we compared the IFSOC system with 2 other systems at SLS. So the current filling pattern feedback system, so based on visible photons and avalanche photodiode, and a reference signal, a reference system based on X-ray photo counting. Yeah, so the system has higher linearity and negligible offset, so then we use it as a reference. On the left side, we see that, so the charge per bunch measurement, yeah, so they, for all systems, match quite well. And on the right side, we show the relative error against the reference system. So you see that in the beginning of the bunch train, we see some systematic error. So we are still investigating why that. We assume that is from the long BPM cables from the buttons to the electronic system. Yeah, but we still investigating why that. But in the second half of the bunch, we can see, yeah, so better results. So we also test the linearity of the IFSOC system and also the linearity of the current system. And so the red curve is the IFSOC system, and the blue curve is the current system. So yeah, the IFSOC has shown good linearity and is smaller offset than the current system. And yeah, so we have a bit more of noise, but we believe that is due to yeah, we are averaging the charge over just 120 microseconds, and the old system and the reference system average the data over seconds. And for the bunch arrival time, so we compared the IFSOC system with the X-ray photo counting system. And yes, again, so we see this systematic error at the beginning of the bunch train, but for the second half of the bunch train, the phase, the bunch arrival time matches quite well with the reference system. Yeah, so yeah, then we come to the conclusion of the talk. So yeah, so we have implemented the 3 dimensions of the multi-bunch feedback with the IFSOC, and yeah, so and the IFSOC has shown to be suitable for at least the basic algorithm of the multi-bunch feedback, and the next steps would be to test the system at the machine at SLS and add features. So advanced features for being diagnostic in the same firmware. We are still using a prototype system, so a evaluation board, and we also have to define the final hardware. And for the filling pattern or charge measurement, so yeah, we tested with this system with the BPM sum signals, and yeah, so they are, and with the comparison with the present systems at SLS, we believe that so it's a promising candidate as alternative or main solution for the SLS2, but we still have to close the feedback loop and work in this systematic errors and noise in the measurements with the IFSOC. So yeah, I would like to thank you for the attention.
Okay, are there any questions? Oh, there's one.
Well, thank you for your nice presentation. My question is, in some multi-branch feedback systems, they have capabilities for real-time tune tracking and single-branch cleaning capabilities. How about in your system?
Yeah, so far we focus on evaluation of this new technology, the IF system on chip. Yeah, so we plan to add advanced features to the feedback, but for now we want to just to verify if this new chip is suitable for multi-branch feedback applications.
Thank you.
Thanks for your talk. Just a question on looking at the future. If you really validate that that's a good technology for the feedback, what kind of platform would you develop your system on?
Yeah, so it's still to be decided. So we favor right now some commercial solution, but we haven't found something that fulfills our needs at PSI. So we are not still not yet decided if we go for developing a board with this chip or in the future, like in the future. There will be more commercial solutions with the chip. So yeah, it's still to be decided.
Thank you.
Okay, I don't see any more questions, so I'm going to just thank Pedro for his wonderful talk. I look forward to hearing the results of your tests.
Oh, thank you very much.
Okay, so with that, we're going to close the session and let everyone go for lunch. Have a good afternoon.